Good morning. Welcome to the last of our seminars this quarter. It's my pleasure to welcome, and I hope we'll all welcome, Dr. and Professor Kultegin Aydin from Penn State University. He got his PhD from Ohio State and subsequently joined the Communications and Space Science Laboratory at Penn State in 1985, where currently he labors as the department head. It's kind of showing a train of leadership provided by electromagnetics groups. It's true in our department as well. He has worked for most of his career, almost all of his career, on radar remote sensing of precipitation in clouds. His work has been recognized as he's a fellow of the IEEE, and he also serves as an associate editor of IEEE transactions on geoscience and remote sensing. Today he'd like to tell us about estimation of rainfall by observing the attenuation of Ku band spacecraft transmissions to the Earth. Dr. Aydin.
John. Good morning. I'd like to recognize my colleagues, Julio Urbina and Lars Tyrud, and our graduate student Hakan Arslan, who were involved closely with this research, which is ongoing, by the way. Our objective is to evaluate the feasibility of measuring real-time rain accumulation using available geosynchronous satellite signals such as the DirecTV, Dish, and so on. And as you probably know, there are millions of these signals that are coming down to various locations in the continental U.S. So why do we want to measure precipitation? Well, it has a great deal of impact on a number of critical areas, including agriculture. Farmers need to know how much rain has come down and what to expect. Climate modelers need rainfall accumulation as input and understanding rain processes as well. Water resource management, of course, it's clear, as you can see in the little diagram here from NASA. The water cycle, the precipitation is part of it and brings down the water from the atmosphere through runoff into streams and rivers and lakes and so on, and to underground water. Flood prediction, measuring real-time rain, as well as over a period of a few days is important for flood prediction, including flash flood prediction. And the National Weather Service does send out these warnings and based on radar measurements. It's also important for communication link design, knowing the rainfall statistics across the globe, wherever the link is going to be utilized, knowing how much rain is going to be coming down and the expected attenuation throughout different seasons in the year is critical for these designs. I'll have just a couple of formulas in my presentation. This is one of the slides, and there's one more. Here we see the definitions of the specific attenuation. That's the loss of signal in dB per kilometer, and rainfall rate in millimeters per hour. And as you can see, both of these parameters are related to the raindrop size distribution, N of D, D being the size of the raindrops, which is variable. The attenuation depends on the extinction cross-section of the drops. The extinction cross-section is effectively takes into account both the absorption and the scattering cross-sections. In other words, when an electromagnetic wave is incident on a raindrop, part of that energy is absorbed in the drop, part of it is scattered out from the propagating wave. And the extinction cross-section includes both effects. Rainfall rate is related to the volume of the drops and the terminal fall velocity. If you look at these two expressions, as you can see, if you can express, for example, the extinction cross-section as a power of the size, you would have a certain moment of the size distribution leading to the specific attenuation. Similarly, if you did the same for the terminal fall velocity, you'd have some similar version for the rainfall rate. If these two power relationships were very similar, in other words, D raised to a certain power, then the relationship between A and R would be a linear one, independent of the size distribution. And that would be something desirable, but unfortunately it doesn't happen in most frequencies. There's one frequency that it happens in the microwave band, millimeter wave band. That's around 35 gigahertz, which I'll talk about in a few moments. Here are some calculations done using ME series, assuming spherical drops back in the late 70s. As you can see around, as you increase the frequency, the rain attenuation increases. And it levels off and starts to decline after a few hundred gigahertz. And of course, you know that once it gets into the visible range, it's very low. We can see through the rain. At 10 gigahertz, you can see, depending on the rain rate, you could have several dB per kilometer attenuation. And that could be significant if you're observing with such an X-band radar, a storm system. You may not be able to see the backside of a heavy rain cell. Here's a set of relationships that were derived from the work that I just mentioned, based on some different drop size distributions. And there's also a model from the International Telecommunications Union that's also plotted. And as you can see, they all seem to give different results depending on the rain rate. So the choice of the model is also critical in estimating attenuation from rain rate or vice versa. Here's a look at just a couple of papers from the 1940s onward related to attenuation. The earliest ones are due to Ride, who did a lot of calculations using the ME series expansion in a time when there were no computers. They did them by hand. And the reason they were interested in it is because after World War II, the radars that were developed were found to be potentially useful for observing weather phenomena. And, but at X-band, for example, they were experiencing loss of signal, and they were trying to understand what was causing that. And that continued with other work in the 50s and 60s. And for example, in this paper, Medhurst, they were looking at the effects of loss of signal and communication links. Interestingly, this is one of the first papers that, by Harold, that looked at attenuation as not as a problem, but as something that could be used to find something out for estimating rain. And the choice of the wavelength or the frequency is the one that I just mentioned when both attenuation and rain rate have the same moment of the size distribution, which occurs at 35 gigahertz or 8.6 millimeters, making it independent of drop size distributions and a very nice way of estimating rain. Oguchi was one of the first to look at the attenuation and phase effects of raindrops when you consider them in their more natural form, which is not spherical, which is more like a spheroidal particle. So its vertical and horizontal axis are different. Further work, this one we just mentioned, they still were using spherical particles, but it gave a pretty good idea of what to expect over a wide range of frequencies. And in the 90s, there was, for example, an experiment by NASA called the ACTS, Advanced Communication Technology Satellite, for generating statistics of signals at 20 and 27.5 gigahertz. But essentially, they were just trying to understand the effect of rain on these signals. In the 2000s, this is just one paper, but there's a trend to look at terrestrial links and some of these short links in urban environment for wireless communications to be used for estimating rain and other things, actually. But rain is one of the critical parameters that was promoted, and a number of papers have come out since, and still in the experimental phase, but this is a terrestrial link utilizing attenuation for rain estimation. So what methods are there that are presently used for estimating or measuring rain? The most common one, obviously, is the rain gauge and the strometer, which is not as common because it's a more expensive equipment measuring drop size distributions. But rain gauge essentially measures the accumulation of water falling in a certain part of space. It's a point measurement where you put the rain gauge, that's where you're measuring it. Radars, ground-based and satellite-based radars are doing this at this time, and the terrestrial microwave links that I just mentioned, which is an experimental stage. Rain gauges, here's one example, a tipping bucket rain gauge where there's a funnel which collects the raindrops and then funnels it into a flipping container, which it has a certain volume that it can take and then flips and empties that side. And then when the other one fills up, it empties that. So every flip that we know how much volume of rain was accumulated, so you can record it. It's a working principle, simple. It measures rainfall accumulation directly. That's a very direct measurement. The disadvantages are it's a single point measurement. Extrapolating to wide areas requires many of them, and their maintenance and so on. It is costly, and it's difficult to deploy in urban areas because, well, they're not very useful on top of buildings. The weather radars, the National Weather Service has about 160 of these what's called NEXRAD, Next Generation Weather Radars. They provide high spatial and temporal resolution. Their coverage area is large, over 200 plus kilometers. And recently, they've all been upgraded to have dual polarization capability, which will add to the precision of their measurements. Their disadvantages, if you want to list some, are that they are costly. And there are issues related to the ZR relation, Z being the reflectivity factor that the radar measures, and the relation to rain rate. There are problems with that in terms of errors, but the polarimetric capability should improve and help make more precise measurements. There are issues with beam blockage, except in the case of one of the polarimetric variables measurements, which is the differential phase shift, which is immune to beam blockage. And then there are issues which with the bright band, when the radar beam goes out to large distances, the beam spreads, and it includes a larger portion of the atmosphere, and if it intercepts the bright band, the reflectivity you're assuming it is coming from rain is actually coming from melting ice particles, which could be higher. Well, typically in the bright band it is higher, and you would have a bias in your estimates of rain from the reflectivity. Space-based radars, the TRIM Tropical Rainfall Measurement mission had a radar at KU band, and that was launched back in the late 90s. Recently, a new system has been put up for the global precipitation measurement of NASA, where they have two radars, one at KU and the other one at KA band. And the global coverage for the TRIM is just focused on the tropical region, whereas for GPM, it's a worldwide coverage. It has two frequencies, 13.6 and 35.5 gigahertz. Both of these frequencies do suffer from rain attenuation, but there are ways of recovering from that, and having both frequencies helps immensely in that recovery. The disadvantages, the GPM radar comes back, the revisit time is 3 hours, around that on average. For TRIM, it's 12 plus hours, and it's focused on the tropics. It doesn't cover the rest of the world. There are issues with single frequency measurements, which TRIM is relying on. Many papers published in this regard. That's why this GPM was put up to avoid those. They're costly and hard to maintain, and GPM is fairly new, and I think it's still being tested out. Here's a depiction of what the GPM is doing. They have the two radars have a different swath that they scan, but they're essentially looking, when they overlap, they're looking in the same region. Here's sample measurements that NASA has on its site. And actually it's a Japanese, I think it's JAXA, the Japanese space agency, and NASA. It's a joint effort, this TRIM and GPM. So that's why you see the different lettering here as well. So this top figure shows you the 13.6 gigahertz measurements. The measurements are from top down. And this is at 35.5 gigahertz. And if you look at the same cell, for example, you can see that the 35 signal pretty much almost disappears toward the bottom of the cell, whereas in the lower frequency, it makes it down there, even though it's still being attenuated. And finally, the terrestrial communication links. There are advantages. They're easy to install in urban and hilly terrain areas where radar coverage is problematic. Probably in this vicinity, that would apply. They can provide reference measurements for urban areas for meteorological radar. All these are complementary techniques that are being used. They're not a solution to the problem by themselves. Their disadvantages are that they need line of sight. the transmitting and receiving antennas must see each other. They're limited to areas where such links are available, or they require additional infrastructure to put them on towers or buildings. And they suffer from multipath propagation, which you need to deal with. Okay, so this is what we're proposing, a satellite signal going through the atmosphere. And as it goes through the rain, it attenuates. Most of the attenuation happens through the rain. Attenuation in ice is much smaller than what happens in rain. There is a region called the melting layer, a few hundred meters in depth, which can be which it does attenuate and contributes to the attenuation, which you would not be able to separate from the rain attenuation from these measurements. So that needs to be considered as a complicating issue. You can also observe the rain with a radar if you have one close by, which we happen to. In State College, there's one National Weather Service radar about 18.5 kilometers away. And we utilize those measurements to see how our interpretations of this attenuation relate to what is measured with the radar. So here's a map. This is State College, where Penn State is. On top of one of the EE buildings, we have an antenna for the receiver. And about 18.5 kilometers away in Black Moshannon State Park, on top of a hill that's about 700 meters or so high above sea level, there's this radar facility. In fact, this is a Google Earth view of that. These other pictures are not from that same radar, but as I said, there are 160 of them across the US, and they all have the same tower and other structure. So this is what they would look like in the Great Plains. I think this is from Oklahoma. This is inside the radome. This is the reflector. It's about an 8.5 meter diameter dish. And here's, you can see a technician changing the light bulb on top of the radome, how it compares to the reflector. This is the second slide that I'll be showing you with the formulas. Let's just focus on this radar reflectivity, which is what all these radars fundamentally measure. It's based, if you look at it, it essentially derives from the scattering amplitude matrix. If you have an electromagnetic wave with that's polarized in the V and H directions, and if you want to visualize what V and H is, if you're transmitting along parallel to the Earth, H is parallel to the Earth and V is orthogonal to it. And if you change the orientation of the radar, they just follow that. So when you transmit such a wave, the scattered wave also has both polarizations, and you can measure each one separately. And from one of those measurements, you can derive what's known as the backscattering cross-section at that polarization. You transmit H, receive H. And this ZH relates to that parameter, that backscattering cross-section. And again, the size distribution. So as key here is the size distribution, which appears in all these parameters. In the future plots that I have, I'll be dropping this subscript, not to confuse things further. So as I said, the signal going through the atmosphere goes through clouds and the clear atmosphere where there's water vapor, oxygen. And if you look at the level to expect from water vapor and oxygen absorption, around 12 gigahertz, it's less than 2 0.02 dB per kilometer. So it's much smaller than what you would have in rain, as you can see here. It could be a dB or more, or a fraction of a dB, but 0.02 is much smaller than that. Okay, so here's a measurement that was taken back in September 7, 2011. The plot on the top is the carrier to noise ratio from the receiver. And as you can see, the signal drops when it goes through rain. And the bottom blue plot shows you the rain rate that's derived from a rain gauge that was on the roof. And it pretty much follows the attenuation, or the attenuation follows it. You can see the three different events there. But since this is a point measurement, it's not the best thing to compare with in our case. Sometimes you may end up with a good result, sometimes not so great, because it's a point measurement, whereas the satellite link path is a line several kilometers long. So you're measuring the rain along that path, and you're comparing with a point measurement, which is almost like comparing apples and oranges if you want to be precise. So what we did was we compared the signal attenuation of the satellite signal to the attenuation predicted from radar measurements. Now, how did we do that? We took the radar reflectivity, obtained the rain rate, and then from the rain rate we obtained the specific attenuation, and then added it up along the path. And kind of like this, this is this satellite link, and then the radar intercepts the path. Since this is not a research radar, it's an operational system. It has its own, it does its own thing. Every 30 seconds it rotates, changes its elevation angle, and about every 5 minutes it gets back to the lowest level. So we developed a method to make use of every time it intercepts to derive what happens along this entire path. So when it intercepts, it passes on a plane which, if you projected this path, you would be able to obtain the corresponding rain rate at those locations on the projection. So doing that and utilizing a number of different ZR and AR relationships, and I'm just putting these up to show you that this is just a few of them that we've taken, probably some of the more popular ones. The one at the bottom is what the National Weather Service uses for estimating rain from their reflectivity measurements. And these are different size distributions that lead to these AR relationships at this 12.6 gigahertz. There are many more ZR relationships. If you go back to a book by Batten from the late 60s, he has maybe close to 200 relationships. But that's one of the problems with these VR relationships, as I said. So using here the Marshall-Palmer relationship, ZR, in both the attenuation and the reflectivity estimates of rain, we obtained a comparison for satellite attenuation and radar prediction of that attenuation. And you can see that, there's a good correspondence, although on various occasions it's not identical, which we don't expect it to be. We have to assume a certain path length for the rain, or effectively some effective rain height. And changing that, as you'll see in a moment, changes all these predictions. So what we really want is the rain accumulation. That was our goal. So with the radar, we can use the reflectivity measurement and estimate rain along the path, satellite path. With the satellite signal, we have the total attenuation. If we know the path length, given a rain height, we know the path length, then we can we can derive the specific attenuation from which we can get the rain rate and then the rain accumulation and compare the two. So if you do that, this is what you end up with. This is not a comparison at this moment. This is actually comparing the radar estimates along the path for all those different ZR relationships. And as you can see, they could be significantly different. Maybe here, if you took this relationship relative to that going on both sides, you'd be getting at around 25 to 30% error, which is not bad for rain estimates. Here's the corresponding satellite rain estimates based on the different AR attenuation rainfall relationships. And as you can see, there is a difference between the relationships in the final rain accumulation, but it's not very large. This dotted line shows the radar estimate based on what we call the ZR relationships for thunderstorms. Now, if you did the same thing using the Marshall-Palmer relationship, this is what the radar would estimate, and these are what satellite AR relationships produce. Okay. So now here's one of the problems with, or one of the challenges, I should say, with the satellite rain estimates. You can see if you change the effective rain height from 3 kilometers to 4.5, 4.5 being the one at the bottom here, and the 3 kilometers is the one at the top. So there is a significant difference in the rain accumulation depending on what you utilize as the rain height, effective rain height. So determining the effective rain height is a challenge, and it's something that needs to be addressed if this method is to be viable. Statistics can be derived for these rain heights, or they could be measured in close to real time with polarimetric radar, which I'll show in a few moments. Okay, so getting back to the same slide again, I want to introduce a few other parameters, one called the differential reflectivity, and some of you may know it was introduced by Tom Seliga, who was a department head back in the early 90s here. It's a parameter that's used extensively in all weather radars across the world today, in all research radars, and all National Weather Service radars have been upgraded to make this measurement. They also make, well, it's essentially the ratio of the reflectivities at horizontal and vertical polarization. And they're different because raindrops are oblate spheroidal, like a hamburger bun. So the horizontal has a different return than the vertical. And looking at the horizontal to vertical, you get an estimate of the oblateness of the particle. And it turns out that there is a relationship between the oblateness and the size of the particle, which gives you, hence, an estimate of the size of the particle. So it's useful for measuring rain when you combine it with this reflectivity. But it turns out that it has many other uses as well. It can differentiate ice and liquid water regions in precipitation very nicely, like day and night, which you can't do with just reflectivity alone. There's also another parameter that these new radars measure, and it's the correlation coefficient between H and V returns. And in rain, this correlation is very high, over 98% and higher. When you start mixing different types of particles, for example, where in the melting layer, it drops. And if it's similar type of particles, it rises again. So it's a nice differentiator identifier of a melting layer or melting ice particles or large ice particles. And then finally, another parameter that these radars measure, and they've just been upgraded last year, by the way, what's called the differential phase shift. It's the differential phase shift between the H and V polarizations, between these two terms here. And it's the specific differential phase shift, degrees per kilometer. It's based on the forward scattering parameter. So here, when we use it in this formula, it's backscattering. But if you use it, you need to use the corresponding one for the forward scattering. And it has very interesting characteristics. It's immune to beam blockage, antenna calibration, and so on. Okay, so here's some measurements actually from a recent event, March 29. Here we estimate the rain the attenuation using the Marshall-Palmer relationships and at a 2.5 kilometer rain height. In spring, the rain height is lower than when you get into summer. And we actually have some reason why we chose this, because we were able to look at the polarimetric radar data, which I'll show in a moment, that can identify the melting layer. Okay, so here we've taken the melting layer to be at 3 different heights, 1.5, 2, 2.5 kilometers. And you can see the effect on the satellite measurements on these dashed lines. It's significant, so it's knowing that rain height is critical. It is not as critical for the estimates for the radar. They're very tight. And here we've used the weather radar relationship. Okay, so if you introduce the polarimetric variables, they spread out the estimates from the radar. The ones estimated from reflectivity alone are these top 2 ones. And here you have the parameter that's estimated from differential phase shift. And here's a combination of reflectivity and differential reflectivity in this color here. And this one utilizes differential reflectivity and differential phase shift. So even the polarimetric variables seem to produce different accumulations. This is another day from last year, earlier on when they put in the polarization capability. This is an intense rain event, and as you can see, depending on what you choose as your effective rain height, you can have a range from 38 to 52 millimeters of rain accumulation. But even that range is not too bad. If you introduce the polarimetric variables, you can see that they also have a range, which ideally you wouldn't be expecting to be as large. So we're wondering if there are issues with some of the polarimetric measurements that they're providing. Maybe some calibration issues or whatnot. But since this is all new and people are just using this data, issues that arise will probably be corrected in the coming months. Okay, challenges and future work. Well, one of them is the estimation of effective rain height, which relates very closely to the estimation of the melting layer attenuation. With the satellite signal itself, you can't separate them out. So somehow you need to develop some statistics or some effective way of incorporating the melting layer attenuation into that rain estimation. There's another issue that I didn't touch on, but it's important when you have light rain, and that's when to be able to differentiate wet and dry periods. There is a fluctuation in the background signal level, which could resemble what you may have in very light rain, and if this happens over an extended period, like a day or so, you could end up with accumulations that are unreasonable. Another thing that needs to be looked at, which could help with the light rain problem, is these satellites also transmit at higher frequencies. This one that we dealt with was 12.6. There's one around 18 gigahertz. The attenuation there would be higher, and as it goes through lighter rain, and it may be able to pick up and help with the light rain aspect of these measurements. And of course, a bigger challenge is extending these to multiple links. There's millions of them across the U.S., and if you just take one big urban area, hundreds of thousands of receivers, how would you utilize all of this? It's a big data problem, as you can imagine. But it's something that could be very useful for complementing both radar and other techniques that are used for estimating rain. And of course, an issue that we still haven't addressed here is we've been just looking at the rain along this path of our link. How does that extrapolate to an aerial rain accumulation? That's a major issue, but that same issue exists for terrestrial links, and people have been working on them, extrapolating several links to an area that's not necessarily covered by the links themselves. So that work requires further evaluation and some statistical analysis there. And I'm getting to the end of the presentation, but I just wanted to show you how these new radars can determine where the melting layer is. So here's a reflectivity field. The radar is at the origin here. This distance about 20 kilometers. So that would be a 20-kilometer radius, maybe. The elevation angle in this case is 0 degrees. So the higher intensity areas, you have higher rain coming down, lower rain. So if you elevate the radar beam to 10 degrees, the same reflectivity field looks like this. So at around close to 20 kilometers away, it looks like there is an enhanced reflectivity band. So let's focus in this, I forget what the, okay, so here is the same measure, same scan, but with the differential reflectivity. And even in the differential reflectivity, you can see an enhancement. This is common in bright bands, okay? An enhancement in the signal. And if you look at the correlation coefficient that we defined earlier, there's a reduction in that same region from other areas. So combining these at 30-degree azimuth angle, in other words, right around this region here, you can, if you plot the correlation coefficient, these are the green dots, and you read them from this right axis. So it's very high correlation, close to 1, but in a certain region, it drops to 0.8. And if you look at differential reflectivity, which is the left axis, right around that same region, there's an enhancement in the differential reflectivity. And then it drops in the ice region, and it is lower relative to the melting layer in the rain, but it's higher relative to the ice. So the combination of these two, you can see that this would be the bottom of the melting layer, and here you would have the top of the melting layer. So you can get an estimate of the melting layer. And there is work along these lines. People are comparing with models and other types of measurements, getting the lower and the upper locations of the melting layer through these techniques. So, in conclusion, the attenuation along a commercial satellite link was shown to have potential for estimating integrated rainfall accumulation along that path. There are several challenges which I just noted, and there are possible approaches to overcoming these challenges, and they're in the previous slides there. That concludes my talk. Thank you.
Are there any questions for Professor Aydin? Yes.
Why aren't rain gauges useful on top of buildings?
Well, the question is, why aren't rain gauges useful on top of buildings? The idea is to determine the amount of water that's falling to the ground. The building structure themselves could deviate the rain as it's falling. So it's the aerodynamics of effects that on top of these buildings that and other structures that may be in the vicinity of this rain gauge that you place that may bias the measurements. So typically, either they'll be situated on low buildings, or preferably the ideal would be in a on the ground, flush with the ground.
In your talk, you mentioned mostly the detection and measurement of rain. What issues come up if you're trying to measure snow?
Yeah, we've looked at that. We've looked at the signal, the same signal at 12.6 gigahertz when it was snowing pretty heavily, and the attenuation is not very significant. So when it's not melting, it's not significant. If it was melting snow, there would be noticeable attenuation.
About how many different geostationary satellite illuminators do you think might be useful?
In what sense?
In the sense of having sufficient power and constant power output, appropriate frequencies, things like that. Is it? I really don't have a sense. Is it 10? Yeah. Is it 100?
I don't either. We just utilized the DirecTV signal. We weren't using their receiver. We had to purchase a separate receiver that would be able to output the signal before it goes to the automatic gain control and all that other things that they do, processing.
Are there any other questions for us? Mr. Shimara?
You mentioned the estimation of the rain height. Is that done by measurement, or is that how do you?
Yeah, it could be, as I showed with the radar data at the last few slides, could be done with the new polarimetric radars with those differential reflectivity and correlation coefficient.
It seems that rain accumulation depends on rain height. If you have a different estimate of the rain height, does that change your result?
It does. That's why a good estimate is needed of the rain height to get reliable interpretation of the attenuation in terms of the rain rate or the rain accumulation.
Okay, well, if there are no further questions for our speaker, thank you very much, Dr. Guy.
Okay.
Come down if you like.